Good afternoon, everybody. This is the last presentation for Young Sanseco webinar series. And the title of my presentation is Single Source Energy Balance Models Evaluation and Actual Evapotranspiration Estimation for a Rotational Cropping System in Southern Italy. Basically, I'm a PhD student from University of Molise and University of Tuscia. It's a consortium, and these are my advisors and affiliations. Now moving to the next slide. So basically, under this topic, I studied evapotranspiration, which is an eco-hydrological process. As you can see, this is the central flux of hydrological cycle. I mean, more than 60% of the precipitation, basically, ET process is basically consuming this precipitation. So it has the largest share of the water outflow from the vegetated land. And this information, the ET information, is really important because it gives the consumptive fraction of the water used in the crops. But ET is really difficult and very challenging to estimate because there are lots of spatial variability involved, like there are some different topographies, so soil moisture condition frequently changes, different vegetation types have different responses, and then there is a wind patterns that dragging the vapors from over the canopy surfaces. Well, in case of crop water demand, or in case of the water estimation for crops, we found that soil moisture and ET, evapotranspiration, both these variables, they regulate these flux interactions at the surface and atmosphere interface. And this is basically a central flux for improving the mass and energy balance in agroecosystems. And if you really know the ET, you can easily connect with your system that how much water you need and what crop type you need over your land to control the water amount to the how to control the irrigation amount to the crop. Well, why I selected the southern Italy, because it is this site is falling in the Mediterranean region, and this Mediterranean region is a hotspot for climate, and there are frequent changes are happening. The most important is the precipitation decline and the temperature increase. And the climate forecast study, they have got the results about that there are expected in 6.7% increase in evapotranspiration expected in this over this region. And then because evapotranspiration is truly, it's a meteorological process, it is truly connected with the land and atmosphere interactions. So there are lots of uncertainties involved in estimation. The major estimations uncertainties that are coming, if you see, is basically the variability in irrigation practices, and then the soil heterogeneity. This is contributing into the evapotranspiration prediction more than any other source. Like, for example, in case of climate, it's 5 to 7%, and in LAI in case of 6%. So estimations are really changing because of irrigation differences. Well, recently there was 2-degree initiative by ICARDA, as I belong to ICARDA. So there was a meeting at the regional network, and they identified that basically this region is suffering because there are increased rainfall variability, especially in the springtime, which is the growing season for many crops. And this region is also experiencing the low agricultural productivity because of climate variability. And because of this water stress, they are also putting a more immense pressure over the irrigated networks and irrigated irrigation sources. So the scientists in this region, that are working on, especially on Middle East and North Africa, they are trying to provide those farming systems which are diversified, so which can really tolerate the water stress. If you see ET estimation, there are two basic approaches, one at the local scale and at the stand scale, and other is at the larger scale. Larger scale is really important because you really want to know the complete picture of the of your water fluxes and energy fluxes. So if in case of ground-based measurement, that is only giving you a 1-point measurement, it is only giving you a site location information. There are some lysimeters, there are eddy-covariance, very famous, and then there are over the eddy-covariance, they use Bowen ratio energy balance closure methods they applied. And then they have soil moisture measurements instruments, neutron probe, gravimetric. There are lots of options for the ground data. And for remote sensing approach, they basically derive all these land surface parameters from the satellite image and then apply the energy balance equation over that. And after all these energy balance algorithms and all these calculations, they get evapotranspiration maps. And you can get these maps frequently on daily basis, or you can interpolate on weekly basis. That depends on the frequency of the satellite image you have. So based on my study, I was mainly focused on a single source model. The concept behind this single source model is that it only considers, this approach is applicable only for homogeneous surface, where you have, where you assume that there is no heterogeneity involved, and where you have, it's single source, it means it's considering only a single layer, that it's not differentiating between the soil and canopy. Well, there are also some models, two source models, TSAB, it's very famous. It has two layers, dual source models, and it has two separate layers, separate energy balance calculation for soil and separate for canopy. However, in this case, I basically chose three different categorically different models, and they are based on the one common assumption. They consider soil and vegetation as a sole source, single source, and then they deduct these flux turbulences. These are the flux turbulences, sensible heat flux and the latent heat flux. And they deduct this while calculating the aerodynamic resistance and the surface resistance lumped at the top of canopy. So if you see every model has their own algorithms and on their own calculating procedures and with their own assumptions. If we see the simplified energy balance system, this model that it is different. Well, the scheme is same, but it is different in this aspect that it does not need hot or the cold pixel manual calibration. Neither it needs it. It just simply estimate the sensible heat flux based on the planetary boundary layer and the wind speed profile. Other than that, it has an excess resistance term, which computes the roughness length of the heat and momentum, which is different for the canopy and then soil. So if you see the derivation, it basically estimates the zero displacement height from NDVI, and based on that, it estimate the canopy height and sorry, this is the momentum length, which is derived from NDVI, and from this NDVI they estimate the canopy height, and from canopy height they get the zero displacement height. In case of METRIC basically in SEBS we use only the in situ meteorological data. And in case of METRIC, because it's an automated process, the calibration is also really automated. And so they use the gridded weather data, and from the gridded weather data, they calculate the Penman-Monteith equation. They calculate the reference ET, and this reference ET is then divided by the instantaneous ET, which is calculated by solving this energy balance equation. And then they multiply this, they extrapolate this ETRF with the reference ET to give a complete daily ETA map through METRIC-EEFlux. And this QWater is the assumption behind the QWater is like it does not need any auxiliary meteorological input data. It simply needs one parameter, which is land surface temperature. According to them, according to it, they said all the uncertainties, errors are basically coming from the aerodynamic temperature of the air temperature and the surface temperature. So there is no linearity between surface temperature and aerodynamic and the air temperature. So that's why it does not consider, in this case, in this model, QWaterModel, it does not consider the in situ weather parameter. They solely depend on one land surface temperature. And in this case, they assume that because land surface temperature, if you have a cold pixel, the cold pixel means it's a well-watered pixel, it's an irrigated pixel. So here you will find high ET, and if it is a hot pixel, here you will find low ET. This is the assumption they use, and then you have to just define your in the image which is your Tmax and then which is your Tmin, and then you can calculate ET. Well, my study context was not only to check these models' robustness in capturing the field level ET estimates, and for our irrigated crop, which is irrigated by a central pivot system. Well, under this in this under this site, we have one irrigation impairment incidence in 2009. So we will also discuss in our study that how the eddy-covariance system has sensed these changes. So this is the site. It's a Borgo geophysics site. Is mainly since from 2001 to 2014, there was only a rotational cropping system for maize as major, and which was grown with the fennel and the ryegrass-clover and the grass type plantations. Later on, now after 2014, they totally shift the crop type into alfalfa only. If you see, this is near the Tyrrhenian Sea, and it has a flat terrain with a gentle slope. It has sandy clay soil, which means its clay percentage is 52%. It means it is absorbing more water, and the soil is alluvial because it has a river. It is near the river side. This is the entire methodology. I use Google Earth Engine platform because it's really handy to for calculation of all surface parameters like NDVI, emissivity, land surface temperature. As you know, how do we calculate land surface temperature from when we convert the top of the atmosphere radiance to brightness temperature? And then I also did all the cloud masking, and you know that Landsat 7 has a problem of these stripping of the strips, so where you have no data value. So I also did the gap filling on Google Earth Engine and get the result like this. And for my eddy-covariance data, I calculated reference ET based on the meteorological readings. And from the latent heat flux, the direct latent heat flux that I get from the eddy-covariance system, I applied a Bowen ratio on that, because this is Bowen correction is really needed for to make sure that the energy for the energy closure over the site. Then you can see this QWaterModel is basically a plugin in QGIS. And METRIC-EEFlux, it is developed on Google Earth Engine. It's quite handy to retrieve the product. These are the results. Here I just showed you the overall trend line for evapotranspiration over the surface. You can see this trend line is pretty similar, even though we have a change in, I'm sorry, here I did some, all right. So here, if you see the trend is pretty similar, and we are having a high reference ET and low ETA, which is pretty normal. Then I basically, these panels are showing the different crop cycle period for the different crop types. Here we have a fallow period, and because of this fallow period, we basically lose the soil moisture, which dropped down to 5% only. And then in the next phase, when the maize crop plantation started, we had this irrigation impairment. Like you can see here, the 11 rounds of irrigation here and 4 rounds of irrigation here. The huge difference we found here. And if you see because it's a Mediterranean site, so we have a low precipitation during maize period, so that it needs irrigation, but we don't need any irrigation for grassland because it has plenty of rain is available during winter season. And here one thing, so basically after plotting the entire evapotranspiration trends, we found that this subset is sufficient because it is covering the entire crop, at least a complete crop cycle for a repetition for maize we can see in this time frame. So that's why we selected this simple subset. After that, since we have all this information, so we have calculated ET, we have irrigation amount, and the rainfall, we can easily, we deducted all, you can see the maize 2008 has a different duration. It's from May to August, but for maize 2009, because of this impairment, they have some delay sowing and then delay harvesting. You can see the funnel has water use efficiency higher than the maize in both cases. Well, because it's on rain-fed conditions, there is no irrigation involved. And if you see the LAI in 2008 was higher, well, all these statistics are insufficient because we are only discussing our study period for 2008 to 2009, and this is not our focus, but we just studied what are the physical conditions of the crop here. All right, this blue line is showing the 10 years trend for ET. As you can see, ET is normally higher during summer, and and the black line is showing the latent heat flux calculated from the eddy-covariance system. And these marks are showing the Landsat images, which are total 36 cloud-free Landsat images were used. And under these 36 images, we also remove the clouds. So we also have some deficiency of the data here there. This is the model results. We found that SEBS and the METRIC have some congruence with the in case of the trend line for the ETA, very similar, but the QWaterModel totally behaved differently. Like it has overestimated in one season and underestimated, and then we went into the depth why this model behaved differently, and then we found different reasons from the literature. If you see this R-square value is in case of METRIC, it's 0.64. Well, its RMS error is 1.13, but RMS-E in case of SEBS is low. So, but R-square is 0.58. So you can see, we can basically say that SEBS and METRIC, both they show the same ETA trend with varied magnitudes, but we have got very low fitness for QWaterModel for our site. This is the spatial map, and interestingly, if you can see, this is the eddy-covariance site, and this is its footprint. And if you are using Landsat and if you are applying on the Landsat image as this method is really growing, and there are different platforms, ET platforms are now available. That are providing you the ready-to-use product of ET. When behind that, if you have Landsat, which you need to confirm that your site is also covering this Landsat image is really covering your site or not. So in this case, no. And this is the reason for which we also applied the gap filling method. And in my research, I highlighted for the METRIC-EEFlux that are solely dependent on the Landsat image, that they have not applied the gap filling method on it. So they should really fix it. Secondly, we found some boundary condition variations here, which was only prominent during the maize growth period. So we also identified that okay, this methodology of using the single source models for ET calculation is really good for the tall crops, but it is not really appealing for fennel or the short size crops. Right, and then if you see that we are having a very different output from 3 models, which means you know it's how much it is critical, because your farmer is solely depending on your ET value for irrigation. So small fractional change can also impact the amount of water you are going to put into the field. So this information is really sensitive. In the end, we said that, okay, our soil sensor and our micrometeorological instrument that are installed on the site, they really sense the irregularities we observed in terms of irrigation. And then we also found the low biomass production in 2009. These models are easy to use, though they are now internal calibration is quite easy. People can do it. Although for SEBS, we really have to prepare the data outside, but in METRIC, you have all the data inside. User do not have to do a lot of working in it. And no, neither he, like in previously in historically in previous history, you have to identify the hot and the cold pixels and to calibrate your model. But in this case, it is just automated. So under these conditions, as in for our crop side, when we compare with the eddy-covariance measurement, we found that this method is only suitable for tall crops, but not for the short crops. So this is our message in the end for the study. And with this, I close my presentation, and I'm open for question answers.